we are looking at integration by parts. This is lesson 1, some integration techniques. We're going to start off with something. Consider u times v, and suppose we are going to find its derivative. Well, we can use the product rule. So we have first term times the derivative of the second plus the second term times the derivative of the first. Okay, pretty clear to see. Now let's integrate both sides. Like that. And if I integrate this side, I can write it as sum of, I'm going to write this as dv instead of v prime. And I'm going to write this as sum of integrals, v times du. Okay, just took the integral of both sides. Now, the antiderivative, the integral here, the integral of the derivative, they should cancel each other out. So I have u times v, and that is going to equal the integral of u dv plus the integral of v du. And you're probably wondering, okay, why is this important? Well, if we solve this now for the integral of u dv, then I would simply subtract this quantity from both sides, and I would have u times v minus the integral of v du. So what have I done here? I have discovered or proved the formula for integration by parts. So let's take a look at example 1. This is in your notes packet downloaded before watching the video, so make sure you flip to example 1 or go to the bottom of the page where example 1 is. So if I'm looking at this prior to this lesson, I might try a u substitution. Perhaps I try u equals 2x, but then I realize I can't cancel out the x in front. So this leads to the integration by parts. So integration by parts, what the heck does that mean? Well, we start off by saying maybe this integral here is of the form u dv, and then I have a formula for integral of u dv, the one we just discovered. So if I'm gonna do that, I have to choose a u and I have to choose a dv, and it's helpful if you write it in this exact order underneath the integral. So for simplification purposes, I'm going to start off without any decision making. I was like, well, I'll let u equal x and dv equal e to the 2x dx. Okay, so now in the formula over here, we need a u times v minus the integral of v du. So I see that somewhere in this I need a du, and somewhere in this I need a v. So that means if I take the derivative of u, I get du, which in this case is simply dx. And here, if I take the antiderivative of dv, forgetting about the plus c for a moment, then I'm going to get e to the 2x over 2. And these are the components we need in order to find the antiderivative. So let's take a look. Now, I do a lot of bump bump talk here because it's easier than memorizing this formula. It's bump times bump, u times v. So I go across this way. I say u times v, and this is over 2. Now it's minus bump again times bump, which is going to be e to the 2x over 2 times dx. So again, let me sort of say that differently. I look at this and I say bump times bump minus the integral of bump times bump, and I go sideways. So here I have it. So now I have a new integral part of the problem, but I know how to do that integration. So I'm about to do that as soon as I select my white color again. So come down here. So we have x e to the 2x over 2, that's the first part. Now minus the integral of the purple or pink part, and that's going to be e to the 2x over 4 plus c. This step here is the u substitution, which you should be familiar with. And there we have it. There's our answer. Don't forget the plus c. So a couple things to note, that your choices of u and dv for this first problem were easy, but they're not arbitrary. The idea is you want to pick a dv that you can simply integrate, that has a simple antiderivative, opposed to not knowing how to find the antiderivative. And in u, it's helpful to pick a u that when you take du, it also becomes more simple. And you will see as we go on to some other examples the strategy. So here's example 2 in the notes. So we know we're doing integration by parts because I'm telling you, and that's really what I want you to be able to do. If somebody says integrate by parts, you know how to do it. So we need a u and we need a dv. That's our starting point. I hope you can look at this for a moment and say, well, I just got to pick a u. Let me guess x. And I've got to pick a dv. Let me pick secant squared x. And can't forget the dx. Now, will this work? Well, I have to look at the dv and determine, can I find that antiderivative quickly? And indeed I can. So I'm ready to proceed. So du equals, just like before, dx. And then v equals, do you know the antiderivative of that? Oh, you should. Book of Memoirs. The tangent of x. Because the derivative of tangent of x is secant squared. So now I'm ready to do some bump business. Bump times bump, x times the tangent of x minus the integral of bump times bump. So that would be tangent of x dx. And I'm ready to move on because I have a new integral. This one you may recognize, may not recognize, as tangent of x is the sine of x over the cosine of x. And then I would do a u substitution, traditional u substitution, where u is cosine x, and that would lead us to the following. So first I have x tan x minus the integral of sine of x over the cosine of x, and then again dx with my u substitution. It turns out that I'm going to have 1 over u, negative 1 over u, so this becomes x tangent of x plus the natural log of cosine x plus c. And here is our answer to the problem. Yay, integration by parts. Next, let's take a look at example 3, which is right below number 2 in the notes packet. Here we have the antiderivative or integral of the natural log of x dx. Ooh, we don't have a lot of choices here. I'm telling you to use integration by parts, so you know you need a u and a dv, but we don't have a lot of choices here. What can possibly be? The one thing you don't want to do, don't ever let u equals 1. The reason is, if u is equal to 1, dv is everything else, and I have to find that antiderivative, and that brings me right back to where I started. So we need a different choice. Well, dv has to include dx, and I don't really have a lot of choice. dv has to be simply dx, which means u has to be the natural log of x. Alright, we're ready to do our process. Perhaps you want to pause and see if you can calculate it before me, or evaluate it before me rather. So du is 1 over x dx, and v is antiderivative of dx, which is simply x. Ready for the bump? So we have x natural log of x minus the integral of v du, but do you see that this x will cancel out with this x, and I'm left with dx. So I have x natural log of x minus the antiderivative, which is x, and now I'm ready for my plus c. Example number 4. Here we go. Okay, I need a u and I need a dv. I have some choices here. I'm going to let u equals x squared, reason being, when I take its derivative, it becomes more simple. And then I have a dv, and I can easily integrate e to the 2x dx. So I come down and I have my du, which is 2x dx, and I have my v, which is going to be e to the 2x over 2. I'm ready for bump business, so u times v minus the integral of v du. The 2's cancel out, and I'm left with x times e to the 2x dx. And then I'm ready to find this easy one, simple one, but oh, wait a minute. This is not so simple. This actually requires another integration by parts, the second integral here. So I do again, and this is actually one of the examples we already did. So u equals x, dv equals e to the 2x, du dx, v is e to the 2x over 2. What is extremely important here is that you keep track of this negative. So this negative will be distributed over whatever we find in this yellow box here. Okay, so let's come down here. We have x squared e to the 2x over 2 minus bump business. X e to the 2x over 2 minus the integral of e to the 2x over 2 dx. Distribution is critical. So x squared e to the 2x over 2 minus x e to the 2x over 2. The negative and negative become a positive integral e to the 2x over 2 dx. So the last thing we need to do is a simple antiderivative on the last piece. So we have x squared e to the 2x over 2 minus x e to the 2x over 2. And then we have plus e to the 2x over 4 plus c. Hoo-yah. There we go. Example 4 done. And I'm not really sure what hoo-yah means. Perhaps I meant booyah. Example 5. Hold on to your horses here. This one is fun. So u equals, I have a choice. With you have a trig and transcendental, I prefer to let u equal the transcendental and the dv to be the trig. See? How nice. So I need a du, e to the x dx. I need a v, sine of x. I'm ready for some bump action. So e to the x sine x minus the integral of e to the x sine x dx. Okay, so I have another one. Looks like I'm going to try u substitute, by parts again. So u equals e to the x, dv equals sine x, du e to the x dx, and v is negative cosine x. Again, please be careful with these negatives and distribution of them. So let's come down here. I have e to the x sine x minus bracket e to the x times negative cosine x minus so plus the integral of e to the x cosine x dx. Okay, distribution this becomes minus a minus, so this becomes plus e to the x cosine x. Distribution, this becomes minus the integral of e to the x cosine x dx. And at this point, let me just carry this down. At this point, I hope you see something, and you may be alarmed. So you look at this and say, wait a second. Did I just get myself caught in an infinite loop? Well, perhaps you did, perhaps you didn't. And this is the critical part of the problem, the exciting part. If this were a plus, then you are done. Pack it up, go home, you've got a problem. But the fact that this, well, let me clarify. If this were plus 1, you've got problems. But the fact that this is minus 1, we're okay. Look at it for a moment. What could we do? We're trying to find this integral here. I have it over here, and I have it over here. Do you see? I need to add this integral to both sides. So I'm going to add this to this side and add it to this side. So that's going to give me 2 of them. 2e to the x cosine x dx equals e to the x sine x plus e to the x cosine x, and I think it's a good time to write the plus c. See that? I was left with this because I added to both sides. Now if I divide both sides by 2, I get 1/2 e to the x sine x plus 1/2 e to the x cosine x plus c, and that solves the problem. But do you see something? Do you see that if this were a plus to begin with, then I would subtract that to both sides, and when I subtract it from itself, it would go away, and I'd have implosion. I'd have 0 equals this, and I wouldn't know the actual antiderivative. Actual antiderivative is right here. Cool problem. I know, don't have to tell me. Example 6. Oh, nasty. This is as nasty as they get. Okay, so I need a u and I need a dv. Let's see here. My dv has to be such that I can take the antiderivative. So what would be a good choice? Do you see it? Secant squared x dx. That makes u, the rest of it, one old singular secant of x. Let's see how this bad boy plays out. You want to try it? Go, pause it, try it. See if you can get the answer. It's nasty. Okay, du. Secant of x, tangent of x, dx. V, good old-fashioned tangent of x. So we multiply our bump times bump, secant of x, tangent of x, minus the integral of secant of x, tangent squared of x dx. This is a good time to stop, play around, see what happens. Chances are you won't get it, but you'll appreciate the answer if you try. I'm going to let you pause it. And if you're back, let's see what's happening here. Okay, so I sort of made you think that you would use integration by parts again, but there's a trick to this. The tangent of squared can be written in terms of secant. Do you know this? I hope you do, but sine squared plus cosine squared equals 1. Yay, obvious. If I divide everything by sine squared, I get some identity. 1 plus cotangent squared equals cosecant squared. Same is true if you divide everything by cosine, then I get tangent squared plus 1 equals secant squared. So I can write this tangent up here. I'm not doing any sort of integration technique. I'm just using some good old-fashioned pre-calculus. Secant of x, and then the identity would be secant squared of x minus 1 dx. Let's see how this plays out. So we have the secant of x, tangent of x. Okay, so this has to be distributed, and at the same time I'm going to distribute the antiderivative or integral symbol. So I have minus the integral of secant cubed of x dx Oh, and I'm happy about that. Right? You can see it. Not an infinite loop. Plus the integral of secant of x dx. That's this distribution here. Okay, so I'm feeling pretty good about myself. I'm going to add this to both sides, so I get 2 the integral of secant cubed x dx equals secant of x tangent of x plus the integral of secant of x dx. Do you know this one? Book of Memoirs, Book of Memories. Alright, so we have the integral of secant cubed x dx equals 1/2 secant of x tangent of x plus 1/2. Do you know it? Natural log absolute value secant of x plus tangent of x plus c. Tell me, was that sweet or what? That's the last example of the traditional integration by parts, and the next part of this video, the next video in the playlist, is going to be a shortcut technique that works with certain ones, and trust me, you're going to want to know the shortcut technique.